All right. Welcome back to this part B of lecture 3. So in this, we're going to continue working on some evaluating limits, and we'll get into a couple additional theorems that are very important, very famous, actually, calculus theorems. So let's revisit what we did previously with another example. So here we'll take a look at evaluate the limit as x approaches -3 of x squared plus x minus 6 over x plus 3. Naturally, this is going to be one with a hole in the denominator, right? So notice that both the numerator and denominator are polynomials, right? They're both polynomials, but the limit of the denominator is 0, so you can't just apply the nice rational function theorem that we talked about earlier. So instead, we have to derive. Let's do the derivation. So x squared plus x minus 6 over x plus 3. That'll be our sort of our f of x, the one with the hole. Let's see what we can do with that. Let's see if we can transform that. So we can factor this numerator, right? This second order polynomial will factor into x plus 3 and x minus 2, right? And then nicely when we do that, we can see that you're going to get the cancellation and you get x minus 2, right? So if f of x is equal to x squared plus x minus 6 over x plus 3, and g of x we derived here is equal to x minus 2, then f and g agree with each other everywhere, identical everywhere, except at x equals -3. Right, and so we can apply the theorem that we previously devised. We can say that the limit as x approaches -3 of x squared plus x minus 6 over x plus 3. Well, that's going to be the same as the limit as x approaches -3 of this g function that we identified, x minus 2. And that one we can just simply plug in. It's straightforward. And we get a -5, right? So another application of that very useful theorem. This is a very extremely useful theorem, so that's why we're kind of pushing on it a little bit more. We'll do one more example with it. And so this example, we would say, let's take a look at the limit as x approaches 0 of x plus 1, the square root of x plus 1, minus 1 over x. So obviously, in this case, you've got a hole, right? The denominator this function can't be evaluated at x equals 0. So the limit of the denominator would be 0, so we can't apply the we can't apply the polynomial or the r of x theorem. So instead, let's see if we can find that g function. So we say f of x is equal to x plus 1 minus 1 over x, right? So what can we do? Well, we could multiply the top and bottom by something to see if we can deal with this x in the denominator. We could say something like this. Let's do x plus 1 minus 1 over x, and let's multiply it by x plus 1 square root plus 1. All right, we can do that, right? You can multiply any function by 1 and not change the function. That's just algebra, right? So when we do that, what do we get? Well, you got to kind of distribute here, FOIL this out, right? Kind of think of it as this piece and this piece. When you do all of the multiplication in the top, you get x plus 1, right? Those two together give you x plus 1, and then you get minus x squared of x plus 1 plus square root of x plus 1, and then just a minus 1, like that. And then the denominator, of course, we'll just do it like this for now. You get that. Okay. And then what can we do here? This denominator? Let's go ahead and expand this. And what do we get? We would get x. So the top is just x, right? Now in the denominator, what we end up with is oh, I'm sorry. Yeah. Oh, sorry. Here we go. Sorry, I was looking at the wrong. So clearly the +1 and -1 go away, right? So you just end up with an x up top. So you get x over x times the square root of x plus 1 plus 1. And obviously the x's will cancel as well. And so you get 1 over x plus 1 plus 1. All right, so this would be your g of x. Now, when we look at this function, is it going to be possible to evaluate this at 0? Right, so do we have a problem that we previously had? No, so this function works at 0. Right, so then what we can say is that the limit as x approaches 0 of x plus 1 minus 1 square root that, the x in the denominator, is going to be equal to the limit as x goes to 0 of this guy, of the g function. So it'd be 1 over the square root of x plus 1 plus 1. And that one we can evaluate real easily, right? We can just plug in a 0 there, and we get 1 divided by, this turns out to be 2 down there, so 1/2. So that limit is 1/2. Okay, so there's a couple more examples using that very, very famous, very widely used, very life-saving limit theorem. All right, now the next theorem is one that's pretty interesting theorem. It's got a lot of far-reaching applications. It's one that you'll probably use throughout calculus at different times. It's called the squeeze theorem. It's got a very kind of interesting feature which resembles squeezing. So it's called the squeeze theorem for that reason. And so here's what it looks like. If you have three functions, h of x, f of x, and g of x, and if f of x is between h and g, for all x in an open interval around c, for all x in an open interval containing c, and then we are able to say except possibly at c itself. Then, well, so okay, if h is less than or equal to f, which is less than or equal to g for all x in an open interval containing c, except possibly at c itself, and if the limit as x approaches c of h of x is equal to some value L, which is also the limit of g, okay, then that value L is the limit of f as well. Okay, so you may be able to see why it's called the squeeze theorem. Basically, if you have two functions and a third function between those two, and you're able to say, okay, clearly f is between h and g for all x, right, greater than or equal to, less than or equal to, so it could potentially be equal to these values. And if the functions that bound f both have a limit at c equal to L, then what that implies, what that forces, is that the function f also has a limit at L. Okay, so this is called the squeeze theorem. And we can try to visualize it. I don't have multiple colors, so it'll not be perfect, but you can imagine if this is your h, maybe this is your g function, and maybe below that you've got some other function h, and then f you know is between those two, and let's just say f has a hole. Well, if h and g both have a limit here, right, if h and g both have a limit there and f is guaranteed to be between those two values, well then it has to have the same limit, right? So if the limit of h equals the limit of g, then the limit of f is the same, basically. Okay, now we won't prove the squeeze theorem in this, but this would be one that you would pick up in analysis. It's very nice proof. But what we will do is we'll use it in a clever way to come up with three special limits. And we won't prove all of these, we'll prove one of them, and I think it's a very nice proof. So the first one is the limit as x approaches 0 of sine of x over x. That limit is 1. Okay, so if you take the sine of x, you divide it by x, then as x gets closer and closer to 0 from either side, the value of the ratio goes to 1. That's pretty nice. We'll prove this one in a second. It's got a very nice proof, very elegant proof that uses the squeeze theorem. The second one that is useful would be the limit as x approaches 0 of 1 minus cos x over x. That one is equal to 0. All right, so 1 minus the cosine of a value x divided by the value heads to 0 as x approaches 0. And the third one is the limit as x approaches 0 of 1 plus x to the 1 over x power. And that is equal to, miraculously enough, e. Okay. All right, so these are three special limits that will show up here and there in calculus, and we will see some of them more often than others. But this one here I want to spend some time on. I want to go ahead and I want to walk you through a nice proof of this third limit, and just basically because I want to show you how the squeeze theorem can be used and how it usually is used. It's typically used to find limits naturally, and here is a very good case of it. So let's prove that the limit as x approaches 0 of sine of x over x is equal to 1. So we want to prove that. We want to prove that theorem. Okay, so because this involves sine, naturally we're going to be pulling in some unit circles. So you might be forced to refresh some of your trigonometry. So we're going to start with a nice picture just so we can see what's going on here. So we've got the xy coordinate system. Here's the origin. And let's say we have a unit circle built in here. So I'm going to try to draw this reasonably well. Okay, so this would be like the unit circle in the first quadrant, right? So here you'd have, this would be the point 1, 0. And of course this up here, this point would be 0, 1, and this would be 0, 0. Now let's say starting at the origin, we draw an arc, or sorry, we draw a line exiting the unit circle, and we draw it up to this point. And so there's going to be some angle theta that we've described there. Okay, now this point here is a point of interest. Okay, now if you think about this angle theta and you've been through trigonometry, you know that the coordinate of this point, the value, xy value of this point here, is going to be equal to the cosine and the sine. Cosine comma sine. That's what you've got right there. That's the xy address of that point. So depending on what theta is, naturally. Okay. And let's go ahead and draw a straight line there. So now we have this smaller triangle inside here. We've got all 3 points identified. You've got 0, 0, 1, 0, and cos theta, sine theta. And so that's going to be a triangle, a smaller triangle inside here. And of course, outside of that, you've got this sector, right? So you got this sector that goes from here down here, and then the edge of the circle here. Right? It's very important to note I'm talking about the edge of the circle here and not the straight line in the triangle. Okay, and then you've got this larger triangle out here. Okay, so this is 1, right? We know that. So the address here of this point here would be 1 comma tan theta. Now, why is it tan theta? Well, keep in mind that the tangent of theta is equal to the opposite over the adjacent side, right, relative to theta. And in this case, the adjacent side is 1. And so this would just be opposite over 1, which would be opposite. All right, so that's this side. Now we're talking kind of right triangle trigonometry. So we're kind of moving between unit circle trig and right triangle trig, right? But hopefully you're hanging along. So this is 1. And this would be the opposite side relative to theta. So you can say that this is tangent of theta. So 1 comma tan theta. That's this point. Okay. All right. So now with this drawing we've identified three different shapes which we want to look at. So you've got the first shape, which is the large triangle that we just talked about. Okay, so you've got the large triangle identified by theta. This is 0, 0, and this is 1, 0, and this is 1 tan theta. Right, so that's one object. The other object that we've got is the sector. Okay, that's in between. Okay, so this is a curved line, right? So this is 1 theta, or 1, 0, sorry, and this is 0, 0, and this is cos theta, sine theta up here. Okay, and then we've got the small triangle as well, right? So you've got the small triangle, which looks kind of like this. It's not a right triangle. It's got kind of a curve, or it's more like a it's not a right triangle. Here's your theta. Right up here is cos theta, sine theta, and down here is 1, 0, and 0, 0. Right. So hopefully labeling these all makes it very clear. So it's important to notice that for this triangle here, you've always got this sector. Right, so this one is always smaller than this, right? Like naturally this triangle here, right, that's described here is always going to be smaller than the sector, right? Because it's inscribed inside the circle. So that's, hopefully that follows. Okay, now, so we can talk, so we have these three figures, we can talk about the areas, right? The area of the large triangle, the area of the sector, okay, and then the area of the small triangle. Okay, now just geometrically, we know that the large triangle is going to have the largest area. Okay, and specifically, it's going to be larger than the sector always, right? And it's the case that the small triangle is going to have the smallest area, right? And in between is the area of the sector. So can we figure out what these areas are? Can we figure out what the value of these areas? So does that follow, right? So you've got the large triangle outside, which has a certain area. You've got the sector, which has another certain area, which is less than or equal to the area of the large triangle. And then you've got the area of the small triangle inscribed inside the unit circle. Obviously, that area would be smaller than the sector, right? So you've got this relationship. So you can kind of see we're setting up the squeeze theorem here. Okay. So let's figure out what these areas are. So area of this one is just right triangle, right? So 1/2 base times height. So it'd be 1/2 base times height. So what's the base? Well, the base is 1. And what's the height? It's tangent theta. Okay, so you could think of this one as tan theta over 2. And what about the area of the sector? Well, maybe it's not well known, but the area of a sector is equal to 1/2 the radius squared times the angle theta that sweeps the sector out. And so for us, that translates into 1/2 times 1 times theta. So basically theta over 2. Okay. And then over here, this is a this is the small triangle, and so the area here is sine of theta over 2. Okay. All right. And then, but basically what we're saying here is that the tangent of theta over 2 is greater than or equal to theta over 2, which is greater than or equal to the sine of theta over 2, right? These are the areas. Okay. So if that's true, then we can manipulate, as long as we're using appropriate algebra, we can manipulate these things. And so we've got tan theta over 2, and let's multiply everything by 2 over the sine of theta, and it'll become clear why we're doing that in a second. All right, so we're just going to multiply everything by that factor. So you got theta over 2 times 2 over sine of theta. And you've got sine of theta over 2 times 2 over sine of theta. Okay, now what happens when I do all of that? Well, we get something different here, right? So off to this side, obviously you get 1. And in the middle here, you get theta over the sine of theta. Okay. And what do we get here? Well, remember, tangent is cosine over sine, and so you can basically cancel out the sines, and you get cos theta here. Okay. So we're getting closer here. Remember, the function we're looking at here is sine of x over x, and what we've got here is theta over sine theta. Well, this inequality can be flipped up, can be changed, right? If we can take the reciprocal of all of these things and reverse the inequalities. And so this implies that you basically have 1 over the cos theta, and that'll be less than or equal to sine of theta over theta, which will be less than or equal to the reciprocal of 1, which is 1. Okay, so this is our target function. We have a geometric proof that shows that the value of this function here is between these two values. Okay, and so what we can do is we can use the squeeze theorem here. So specifically, we can say the limit as theta goes to 0 of 1 over cos theta. What's that equal to? Well, cos theta is, what is the value of cosine of theta at 0? It's 1. So this is equal to 1. And that's obviously equal to the limit as theta goes to 0 of 1. Okay, so these two here both have this common limit. That implies that the limit as theta goes to 0 of the sine of theta over theta is 1 as well, which is the result we were after. That's kind of what we were heading towards or hoping to show. Okay, so a nice theorem, a nice proof using the squeeze theorem. And the other ones can be proven as well. I've done one of the 3. The other one I have not done, but it relied on a similar kind of geometric argument, different but similar. So I'd recommend giving it a shot. Okay, let's take just a few more examples, and then we'll call it quits with this lecture. So example, let's evaluate the limit as x goes to 0 of the tangent of x over x. Okay, so this is one where, again, just kind of taking advantage of what we can do with trigonometric functions. So this would be equal to the limit as x goes to 0 of, instead of tangent of x, we can write cos x sine x all over x. Okay, and a more useful way to write that might be to write it as the sine of x over x times 1 over the cosine of x. Right, and then by this point you can imagine what we're going to do, because we know that both of these are defined. This one we just showed, and this one we know we can get to as well at x equals 0. We can pull those apart, and we have the limit as x goes to 0 of sine x over x times the limit as x goes to 0 of 1 over cos x. All right, and of course 1 times 1 equals 1 for that one. Right, so this one is one we just proved. This one is, well, we actually looked at this one indirectly as part of the previous proof, but you know, it's just a straightforward plug-in. And then one more. Let's take a look at one more example. Let's talk about the limit as x goes to 0 of the sine of 4x over x. Okay. So this guy, this is an example where we can't just apply the previous theorem, right? Sine x over x doesn't work here. This is sine of 4x, so obviously the value of the trig function changes differently than it would if it was just sine of x. So let's do the following. A lot of these just kind of require some experience. The sine of 4x over x, well, that's equal to the limit as x approaches 0 of 4 times the sine of 4x over 4x, right? Multiplying the top and bottom by 4. And so then what we can do is we can do this. We can say 4, we can pull this 4 here outside of the limit, like so, and we get this. Okay, so now, right, so what we've kind of done in that step is we've forced the denominator to match what was inside the trig argument. So if we say let y equal 4x, and of course noting that x goes to 0 if and only if y goes to 0, well, we get the following. We could say 4 times the limit as x approaches 0 of sine of 4x over 4x is equal to, well, let's just substitute everything in substitute y in for every time you see 4x. Instead, we could say 4 times the limit as y goes to 0 of sine of y over y. Right, now, obviously, as y goes to 0, 4x goes to 0 too. So this is a safe, a reasonable swap here, right? So you get 4 times, and we know the value of this is 1, right? And so that limit turns out to be equal to 4. Okay. So lots of examples. Obviously, there's a lot more examples we could do. If you go find a textbook for calculus, you'll see that there are, literally thousands of different examples that you could work through. And I would recommend do at least 100. That'll give you'll have a good firm foundation if you can crank through like 100 of these. It just requires a certain amount of experience just to kind of see what is out there and what can happen. All right. Okay, so with that, I will end lecture 3 evaluating limits. Next time, in the next lecture, lecture 4, we'll get into the idea of continuity. And so I did mention already kind of that the reason a lot of these limits are so nice and so clean is because we've been dealing with continuous smooth functions. And so we'll get into that concept a little bit more next time. All right, see you then.